Hello everyone, welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and college or university levels. If you're interested in getting some tutoring or if you're interested in getting some help with your homework, check out the links in the description below. Cool, so today we got a lot of physics to cover. Exciting, as always. So I'm going to switch my screen ASAP fast. And we can begin this physics adventure. Cool, so let's just get right into the fun. Okay, let's get it started. So this is the first question that we have on the menu today, and it is presenting the following situation. So we have two small spheres of mass m. We don't really know what they are, well, not at this point, and they are carrying absolute charge q. And they're suspended by massless threads with length L, as shown. Now, it's not quite shown here in the question, but here we have a diagram that kind of represents what's going on. I'll redraw that later, but let's keep going through this situation. The distance between the two anchor points, and those are the two balls on the end of the strings. The distance between them is equal to d, and at equilibrium, when they're not moving, the two spheres lie in the same horizontal plane, meaning that they're like the same height. It'll be more clear when we get to the diagram. The threads each make an angle of question mark. Let's just say that's theta, because that's more common for dealing with angles, with the vertical. Okay, so let's actually draw this situation so we can kind of have a better understanding of what's going on, right? It's always good to visualize. So let's get some, we have two spheres with mass m. At this point, we don't know what m is, but that is not nothing to be worried about. And they are about the same height. The distance that separates them, or they have to be the same height, this is d. So that's the distance that separates them. And they are both attached via string to a anchor point. Okay, so the distance between them, suspended by massless threads of length L. So L is going to be this distance right here. And it'll be just the same on the other side. I'm not going to draw it just so that we're not too cluttered. But yep, L is like the distance that the respective balls are away from the anchor point of the wire. Okay, and anything else? They have the charge Q, and we don't know what Q is at this point. Nothing to be worried about. And they make an angle with the vertical. What that means is if we were to have a vertical hypothetical line like this, this would be the angle and this would be the angle that we're looking for. I'm using the Greek letter theta instead of question mark. I think that's just because there's no theta button on your keyboard. Okay, so part one of this question is asking us, assuming the figure is correct and the charges are repelled from each other. Okay, so maybe let's put forces in red. So here we have an outwards force. So both of them are repelled from each other. And let's just call that Fe because both of the particles are charged. That means that the force that is like trying to separate them from each other is got to be an electric force. That's why we're going with Fe. Okay, so yeah, that's pretty much what's going on here. So assuming the figure is correct and the charges are repelled from each other, which of the following is the best answer? A is both spheres are positively charged. Let's think about that for a second. We know that when the charges are the same signs, they're trying to get far away from each other. They do not want to be beside people that are the same as them. So if they were both positive, it would make sense that they're trying to get away from each other, just like you would see in the diagram. Okay, so A is a reasonable option. What about B? B is saying they're both negatively charged. For the same reason, it's still it's possible that they're both negative because negatives, they don't want to be around other negativity. They're trying to get away from charges that are the same sign as them. So if they were both negative and they're trying to repel each other, that would fit the diagram and the situation that we're presented with. So B is a reasonable option. Now C is one sphere is negative and one is positive. So when they have opposite signs, they're trying to get closer together. If they're trying to get closer together, they're not going to be able to, hold this like a triangular type shape. They're going to try to like, come together and be close to each other if they're going to have opposite charges. So C is invalid. And D, both A and B are possible. That is correct. And E, none of the above are possible. Well, that in itself is not going to be a possible answer because we got all the possibilities for what the charges can be. Charges are either positive or negative, and it says they have an absolute charge. So the only possible combinations is double positive, double negative, or one of each. And to say none of them are possible, I don't know about that one. So yeah, it's got to be C. D, saying that the charges are going to be the same sign. Okay, cool. So that addresses part 1. I'll just write that out real fast. So Q1, charges must have the same sign to hold this position. Would be attracted with the same sign. Cool, so that addresses question 1. The second part of this question is draw a free body diagram for the left sphere. Okay, so I'm actually going to redraw just the left sphere by itself, and we're going to redraw all the forces on it. Okay, so here we have our mass, and we don't really know what that is, and we don't know what the charge is either, but we can just leave them like that for now. And the first force, well, we already had that on the diagram. We had the electric force because it is trying to get far away from the other charged ball. Yeah, okay, so here we have our electric force. And assuming that we are not doing this in deep space, we're doing this on a planet. I'm probably doing this on Earth. It's my favorite planet. We're going to have a gravitational force. Things are going down for real. Okay, so Fg, and we know that this one is going to be mass times the acceleration due to gravity, and the electric force is going to be K times Q times big Q over R squared. Actually D squared in this case, because D is the separating distance between the two masses. So that's the equation right there. And the last force, well, what's stopping this ball from just falling flat to the ground? It's the cable itself. The cable itself is going to provide a force. We're going to call that the tension force. We're not going to be able to calculate, there's no easy equation to calculate it, but knowing the other two, we could easily calculate the tension force. So let's just call that Ft for tension from rope. And another important detail about this is that this angle here is going to be the same as this angle here. Okay, this is just one line intersecting two parallel lines. These are both making angles with a vertical line, so they have to have the same theta value. Okay, that's going to be pretty important as we proceed. But this is part 2. This is a clear free body diagram of the situation. Are there any other forces? We got gravity, electric force, tension. No other forces in here, nothing else to worry about. We've completely addressed part 2. That's awesome. Okay, so for the horizontal distance, or the next question is asking us to find the horizontal distance between the centers of the spheres at equilibrium in terms of L, D, and or we're also going to need to incorporate mass and charge into this as well. Okay, so what we need to do for this is we know that at equilibrium, oops, let's get a black pen. At equilibrium, net force must be 0. Because if the force was not, or if the net force was not 0, well, they'd be moving. And equilibrium, it means they're not moving. So we've got to have a 0 net force. So what we can do here is we can define our, some axes for directions. We have our y direction going vertical, x direction going horizontal, and we gotta make these forces so that everyone balances out. Okay, now we can see that the electric force and the gravitational force, they're already like perfectly perpendicular or parallel to these axes. Okay, so they're all good. But Ft, on the other hand, we kind of got to break down Ft into its components. Okay, so how we can do that on the diagram, maybe I'll do that in a different color, like blue, is we know that we have a y component, Fty, and we're going to have an x component, Ftx, and we know that those are the sum of Fty and Ftx. They are going to be exactly equal to the overall force that they represent, Ft. Okay, so breaking down forces into their components is a pretty important skill, so make sure that you are familiar and comfortable with that. Now, to write equations for Ft, y, and Ftx with respect to Ft, we know the following. So with the power of trigonometry, we can see that if this was a triangle here, Fty would be the adjacent to the angle, and Ft is going to be the hypotenuse. How do we relate the angle, the adjacent, and the hypotenuse? Do you know? I know. Cosine, cause I know. Yeah, I'm funny. Okay, so cos theta times the force of tension. Okay, and we're going to need to solve for the force of tension, but now that we have the y component, we're one step closer. Now, the x component of the tension, well, it's going to involve the opposite side of the angle and the hypotenuse. I think that our previous one is maybe a sign of what to expect, so maybe we can expect a sign for this one. So sine multiplied by the force of tension, and that will give us the x component of the tension force. Beautiful. So we want to find the net force in the corresponding directions so that we can equate them to 0 and solve for the tension force, and also solve for the electric force. Yeah, so let's first do in the y direction. So to set up an equation like that, this is the procedure that I like doing. So you set up a gamma like this. Not a gamma, a sigma to represent that we're adding up everything. And let's also draw a up direction with a plus to represent that up is our positive direction. Okay, that's going to be quite important. So we know that the sum of all forces in the y direction has to be 0. If it's not 0, it's moving, and it certainly is not moving in this case. So to equate that to 0, we just got to add up all of our y direction forces. So I see that Fg, the gravitational force, is in the y direction, and the y component of the tension force is in the y component. And who's positive? So Fty is going up, and up is our positive direction. So we're going to have positive Fty, force of tension in the y direction, and gravity is going down, and that is going to be negative, because if up is positive, down is negative. Seems reasonable to me. So minus Fg. So with some algebra, we can see that bring minus Fg to the other side, we're going to have Fg is equal to Fty. And we can see that Fg is going to be mass times gravity. That's just going to be equal to cosine of theta multiplied by the force of tension. The total force of tension. That's the diagonal one that we have here. Cool. So this is one step. The next step is we want to do our horizontal x direction forces. Okay, so we're going to do mostly the same procedure, but this time instead of up being positive, we are going towards the right as positive for here. Oops, not y. Fx, and that is the total sum of all that. It's got to be 0. Okay, otherwise it would be moving. Okay, so let's see who's going towards the right, because that's going to be the positive one. So it's going to be Ftx. The tension force x component is going to be positive. It's going to the right. So we can write that as positive Ftx. And in the negative direction, we got the electric force. Okay, so we're going to subtract that. Minus Fe. Cool, so this is a fairly easy rearrange. We can do Fe is equal to Ftx. Okay, so that's pretty cool and all, but we want to write these in terms of the things that we know. So Fe, we're going to sub out for K, Q over D squared, but since we know that the charges on both of these spheres separated from here, it doesn't mention that they're different charges, so they would kind of have to be like the same charge. So we can write a KQ squared over D squared, and we want to equate that to the tension force x component, and we know that's just sine theta times the tension force. Cool. Okay, so now that we have these two relationships, let's square them off so that they're more front and center. What we're trying to effectively do is we need to find the horizontal distance between the spheres, right? We're trying to solve for D given these two equations. Now, it might not be completely obvious how we do that at first, but one thing that we could do is we can equate these both to Ft and make them equal to each other so that we can isolate D. Okay, so if we want to isolate Ft for here, let's call this equation 1 and this one equation 2. So from here, from equation 1, we can see that mass times gravity divided by cos theta is going to be equal to the tension force. And the tension force, if we were to isolate the tension force here, we would do the same thing. It's just this side, the left side, KQ squared over D squared divided by sine. Over D squared, and sine is on the downstairs of that fraction. Cool. Okay, so yeah, so this is where that comes from. Okay, so given these two relationships, we want to solve for D. So you know, we're going to do some quick multiplication and division for some algebra to get the D isolated. So we have D squared if we multiply both sides by that, and if we have K Q squared cos theta, sine theta was still down here, and we have mg. One thing I want you to keep in mind is that cos divided by sine, well, the real relationship that I was thinking about is this, is sine over cos is equal to tan theta. So you see how we have cos over sine? That just means the tan is going downstairs, or just the reciprocal. So D squared is equal to, actually let's get rid of that squared and put everything on the left side, on the right side under a root. So we have K Q squared over mg tan theta. Okay, so given this expression, this is a pretty good way for us to be able to solve for D, the separation distance between the two spheres. Now, you might be able to say, like, hey, like, what if we can't get the angle, right? Like, you could sub out, I actually drew this, just while you weren't looking, we could break down this, like, this kind of makes like an isosceles triangle, and with the power of trigonometry, we can have an expression for tan that does not depend on the angle, but this, since we're going to sub in something that has d inside of it, and it's going to involve like d squared, like this is going to be way more difficult to deal with. So I think at this point it's honestly best to just accept the fact that we will need to know theta for us to have a good ability to calculate the d. Okay, but otherwise, as you can see, this process is pretty cool, and we can isolate for d and have a happy old time. Okay, so now we can move on to the last part of this question. It is asking us what is, or I guess that was like part 3 of the question, the horizontal distance between the spheres. The next part of the question is asking us what is the magnitude and the direction of the electrostatic force on the left sphere in terms of well, mass, gravity. We're going to need to know our charge, otherwise there's no way that we can really know our electrostatic force. And of course we're also going to need to know theta, because as we described earlier, eliminating this theta variable is going to be like way more difficult than is like reasonable for this type of question. Okay, so the electrostatic force, we know that we are going to have, so this is Q4, Fe for electrostatic force. This is going to be equal to K Q squared over D squared. Okay, D being the separation distance between the two spheres. Okay, but D, we already know D from here. So our if we just sub that in, like if we have D squared, we can just get rid of the root. So that's just going to be K Q squared over, now instead of putting this D expression all downstairs, I'm just going to flip it and put it upstairs, and put some of it upstairs. Okay, so here we're going to have mg tan theta, and this will be over K Q squared. Now as you can probably see, we have K Q squared on the top and the bottom here. So we can know that Fe, because those will get cancelled out like that, we know that Fe will just be mg tan theta. Nice and easy. Okay, so that will be our question 4. This is a nice expression for the electric force. The next question, part 5, is asking us what is the value of Q, the charge that is, if D is 30 centimeters, L is 10 centimeters, our angle is 30 degrees, and our gravity is 10 meters per second square. That's a little bit uncomfortable, but we'll deal with that. Okay, so here, given these numbers, we have G is equal to 10 meters per second. That does not sit well with me, but that's what the question says, so we have to deal with that. Our angle is 30 degrees. Our distance of separation is 30 centimeters. Another way of writing that is 0.30 meters, because it's always good to rewrite stuff in base SI. Oh, I didn't realize that you can't see that. Okay, and what else was given? L is 10 centimeters. And 10 centimeters corresponds to 0.1 meters. And yeah, so we were looking to find the charge value. Okay, so all that is left here is the charge, and hey, you see this equation right here? We can use this to find the charge, right? So we know that K Q squared over D squared is equal to mg tan theta. And, well, if we want to isolate for Q, well, we shall do this. So we're going to have Q squared on this side is going to be equal to d squared mg tan theta all over k. And k, oh, they gave us k as 10 times 10 to the 9, which is reasonable. Wait, 9 times 10 to the 9, my bad. Okay, and to put this all under the root, let's do this in the whole other step when we sub in our numbers as well. So d squared, we have 0.3 squared multiplied by mass. What was our mass? 2.7 grams. Okay, mass is equal to 2.7 grams. Another way of writing that is 0.0027 grams. Okay, so let's multiply our mass, 0.0027. Multiply by gravity, and that's 10. Oh man. Let's multiply that by tan, and that shall be 30 degrees. Yep, 30 degrees. Whole thing. Did we have L in here anywhere? I don't think we did have L, so it turns out that sometimes you will get information in your equations that is not particularly relevant. Nothing to be worried about, but I'm not... anyways, okay, let's just keep it moving with this calculation. Times 9 times 10 to the 9 on the downstairs here. Okay, so pulling out my calculator, let's find the results of this calculation. So, under the root, we got 0.3 squared times 0.0027 times 10 times tan 30 degrees divided by 9 times 10 to the power 9. Close those brackets and send them all under the root. And my calculation for this is Q is equal to 3.95 times 10 to the negative 7 coulombs. And it doesn't specify if it's positive or negative, so we're just gonna maybe put an absolute value around here so that you know, either way, this is just the magnitude of the charge. Okay, so yeah, that would address this question. Now here it seems that we don't have the actual calculation for this, but this is what you should hopefully get if you run through this calculation. Okay, so yeah, the above solution does not address all parts of the question. Should calculate the charge to be 3.95. That's not a 3, that's a 3.95 times 10 to the power negative 7, oops, not and, to the power negative 7 coulombs. Okay, but yeah, cool. Okay, so here we have the next question on the menu today, and it's presenting the following situation where we have a fireman has a hose and is directing water to fire at this target B, a very hot situation, and there are two possible angles at which you could, or which the firefighter could spray the water and still hit the target at point B. Okay, and the velocity of the water is 70 feet per second. Okay, cool. So let's just write that out. They use VA. Okay, we'll use VA. I would use VW for water, but you know, we gotta stay with the question and what they gave us, and that is 70 feet per second. Okay, another thing that we want to keep in mind is the acceleration due to gravity. Okay, so gravity is what's causing this water not to just go in a perfectly straight line. So what we're going to need there is gravity, and since this is in feet per second, we need gravity in feet per second, which is 32.2 feet per second. Okay, so the question says that there are two possible angles at which this can be done. And let me kind of describe what would be happening in those two different situations. So here we have our fire person with a hose, and we have a target here. We have 20 meters, no, not 20 meters, 20 feet of vertical distance between them. Let's move that down to make it seem more accurate. And instead of a box, maybe let's just have like a point as a target. Okay, and their separation is a horizontal separation of 35 feet. Okay, so if we wanted to imagine the two possible paths of the water, we got blue, that's a very appropriate color for water. We could have this situation where we're going below the horizontal line, or we could possibly have this situation. Okay, so here we're going to have, let's call that angle U for angle up, and maybe this one, let's call that angle D for angle down. Okay, so we're going to need to calculate these two possible paths, and they're both perfectly valid for putting the water onto this hot target. Okay, cool. So let's proceed by thinking about what's going on here. So this stream of water is going to follow a projectile motion type of situation. Okay, so here's the key: projectile. This is what we want to keep in mind. Okay, so what are some key aspects about projectile motion situations that we need to keep in mind? We know that horizontal component of velocity is constant. Velocity is constant. No horizontal acceleration. Only the vertical component of the velocity is going to be changing. Of velocity will change. Okay, so given this, let's actually break this down into our horizontal side. And our vertical. So our horizontal velocity, let's just call this our x direction. And our vertical, let's call this our y direction. So we have our velocity x, which is always going to be constant. This will be... that'll be one thing that we need. We have our horizontal distance, dx, and we have our time that this will take. And time will be the same for both of them. Okay, so our vertical velocity is going to be slightly different. We're going to have a Vyi for initial vertical velocity, because our velocity is going to be changing along the vertical axis. Vyf, our final velocity in the vertical, our vertical distance, our acceleration, which is going downwards, and our time, which will be the same for both of them. Okay, so time is going to be kind of like that bridge between us that helps us keep these two things in line with each other. Okay, so let's express some equations for this. So we know that gravity is going to be negative 32.2 feet per second, because it's feet per second squared. Because we're going downwards. Okay, so that will be one of the things that we know. Negative 32.2 meters per, not meters, feet per second squared. I'm from Canada, so we use meters over here. Okay, our distances, they are given to us from the diagram. So our vertical distance is minus 20 feet. And our horizontal distance, positive 35 feet. Cool. Another thing that we can keep in mind here is that our initial velocity is going to be determined by our angle here. Okay, so our angle is you know, we're pretty much like, if we have this situation and this is our velocity, we know that we're going to have our Vx this way and our Vy Vyi this way, right? So because with the power of trigonometry, we can hopefully see that given the angle, if we cosine it, that will be our horizontal velocity. So cos theta of Vi, so that's our initial total velocity, and our initial vertical velocity is just going to be sine. And let's say that our angles are going to be positive going clockwise. So here is 0 degrees and here is positive theta, and here is negative theta. Okay, and we'll just need to like keep things in mind, like with the signs and all, just make sure that they agree with our convention here. Okay, so for y is going to be sine theta Vi. Our final velocity, we don't know that quite yet, and our time that it will take, we also don't know that yet, but we know that distance and velocity are related to each other through time. So we know that we can do distance divided by velocity. Horizontal component of the velocity is going to be equal to the time. So we have 35 feet divided by cosine theta Vi, and that will be our time. And because time is the same for both of them, we know that this is going to be the case for here as well. So 35 feet over cos theta times initial velocity. Okay, that's going to be our cos theta on the vertical side of things. Now the only thing that we have left to calculate here is the final velocity, and we know that final velocity, this is our kinematic equation, is equal to initial velocity plus acceleration times time. So if we wanted to make an expression for the y component of this, the final y velocity, we know that it's going to be the initial velocity, so that's just sine theta times Vi, and we know that was 70, but I'll just keep writing Vi so we kind of know where this comes from, and then plus a, in this case negative 32.2 feet per second squared, times time, which is 35 feet, divided by cos theta Vi. Okay, so what we got here is Let's actually sub in VI. So that's for this equation. Sine theta times VI, which was 70 feet per second. Oops, not equals. This is going to be minus, and then I'm going to do 32.2 times 35 divided by VI, which is 70. That's going to be 16.1 over cos theta. Okay, nice and straightforward. So now that we have these relationships, we can hopefully find another equation that is representing for t, and then all that will be left is the different theta values, and then we can hopefully be able to solve for that. Okay, so maybe another kinematic equation that we can use is another kinematic. Okay, so another kinematic equation that we should keep in mind is that the sum of the velocities, the initial plus the final velocity, all divided by 2 times the distance, I think. Divided by 2 times time. Times time is equal to the distance. Now we know what the distance is, and we just figured out the calculation for the final, and we already knew our initial, so we should just isolate this for time, and then we can sub it into this time expression, equate these two together, and then we can solve it from there. And you might need to do some trig identities, but nothing to be worried about. So to isolate t, you can see that t is just going to be equal to 2d over VI y plus VF y, and these are both going to be equal to the other time, the other way that we calculated time, because the time has to be the same for everyone, is going to be 35 feet divided by cos theta times VI. So 35 feet divided by cos theta VI, and that's the total VI. Okay, so expanding these out a little bit more, we can sub out our initial y's and our final y velocities. So our initial y is just going to be sine times initial velocity. Okay, then we have the y component, and we just calculated that here, so that's going to be sine theta times 70. Let's just write 70 sine theta minus 16.1 times cos theta. Yeah, 16.1 divided by cos theta. Okay, and yeah, instead of d over here, we can sub in that number. We know that d, which is the horizontal, the vertical distance, because that was corresponding to the vertical component of it, that's going to be 20 feet. Okay, and 35 divided by 70, that's going to be 2 on the bottom, because VI is 70 meters per second. Oh, I'll write that for there as well. Maybe on the next line. But so here, since VI is equal to 70, we're going to have 1 over, oops, cos theta. Okay, cool. So now we just need to do some math to make this a little bit easier, but you can see that here that these are the same term. So this is going to be equal to 2 sine theta times 70. And yeah, let's bring the bottom of the right side up to the top of the left side. Okay, so we're going to have 2 times 70, that's 140 sine theta, minus 16.1 over cos theta, whole thing divided by 2 yeah, 2 cos theta. That is equal to 2 times 20, that's 40. Okay, so now we can expand this out a little bit more. So we know that this is going to, sine divided by cos, that's equal to tan. So okay, so this is going to be 140 over 2 tan theta minus 8.05, that's 16.1 divided by 2 over cos squared theta. That's going to be equal to 40. Now, something that we want to keep in mind here is that cos squared theta, the reciprocal of that is equal to secant squared theta, and secant squared theta is equal to 1 minus tan theta, or 1 minus tan squared theta. Okay, so substituting this back into our equation here for that, you can see that that cos squared on the downstairs, that will become the secant. So this will become 140 divided by 2, that is equal to 70 times tan theta minus 8.05. And, you know, the cos squared became a secant squared when we bring it upstairs, and that's equal to 1 minus tan squared theta. Okay, and that is equal to 40. So as you can see here, we just got to expand this out, and then we're going to have a quadratic formula type of situation. Okay, so a lot going on in this question. So the 70 tan squared, that's going to stay as is. Then we're going to have minus 8.05 plus 8.05 tan squared theta minus 40 is equal to 0, because we need a quadratic formula this up. So to organize this a little bit better, 8.05 tan squared theta plus 70 tan theta minus 48.05 is equal to 0. So we shall quadratic formula this. Okay, so my calculator is very cool because it can do this for me, but I'm sure many of you may also have calculators that are this powerful, and if you're really extreme, you can probably do this in your mind because you're just so sharp. I mean, you could do it by hand, but you know, it's not always easy. And anytime you make a mistake, it will definitely hurt a lot. Okay, so my A term is 8.05, my B term 70, and my C term is negative 48.05. And solving for this, I get is equal to either negative 9.33, or we also get tan theta is equal to 0.639. Okay, now taking the tan inverse of this, And the same procedure over here, tan inverse, or arctan, times negative 9.33. So this here is corresponds to theta is equal to negative 83.88, and here this one corresponds to tan inverse of 0.0639, and that's going to correspond to 3.65 degrees. Okay, so the signs are a little bit twisted from what we had originally, but we can see here that given our original situation where we had back up to this diagram here, this guy, either you're shooting it like pretty much straight vertical so that it falls back down onto the target, or you're like pretty horizontal and it falls down. So I would say that it is more reasonable to say that this angle right here, the lower angle, is going to be 3.65 degrees. And the upper angle here is going to be 83.88 degrees. Okay, the signs were a little bit twisted, but I think that was just because, maybe it's because of the sign right here, but sometimes the signs are not going to agree, but the magnitudes are what you should really focus on, because that's what's important here. Okay, so yeah, very long process, but still fun. Very, very fun. And yeah, everything is good. Everything is good. Once you just keep in mind this identity, secant squared is this one right here. Secant squared is equal to 1 minus tan squared. Okay, and that will correspond to this situation and lead you to victory. Okay, cool. So yeah, the above solution here, there is no above solution, so no solution above either 3.65 degrees down or 88 or 83.88 degrees up. Cool. Okay, so here we have the next question on the menu today, where we have the following situation. A uniform bar that has a weight force of 165 newtons is supported horizontally by two identical wires A and B, as they are shown in the figure. Cool. And we have a small cube that is 185 newtons that is 3/4 away from the distance between A and B, so closer to B. As you can see from the diagram, the wires are 75 centimeters long, have a mass of 5.5 grams, and both of them are simultaneously plucked at the center. So we're trying to figure out what is the frequency of the sound that will be produced from them. It's kind of like a guitar. I got a guitar right there. Guitars are my favorite instrument. Pretty cool. So let's actually draw a diagram of this, and then we can put on the forces, and with that we could you know, get the answers that we need, because the fundamental concept that we need here is oscillation. Oops, let's get a black pen. Oscillations in strings under tension. Okay, the equation that we're looking for in this situation is this equation. Okay, so the frequency is the tension over mass times the length of it. All of this is under the root, and that whole root is divided by 2L. Okay, so this is the equation that we need to use, and the only thing that we're missing is t, because everything else was given in the question. Okay, so when we think about, let's just identify what we had from the question. Our mass is the mass of the string or the wire, so it's 5.05 grams. It's 5.50 grams, and that is equal to 0.0055 kilograms. Right? It's better to work in kilograms. Base SI, that's the way to go. Our length of those wires are 75 centimeters, also known as 0.75 meters. And yeah, now we just need the tension. Okay, so let's draw a free body diagram of this situation. Okay, so here we have tension A, our left side. Here we have our right side, and let's call that tension B. In the exact precise middle of here, we have a downwards force of, let's just call that weight WB for weight of the bar, and then 3/4 of the distance. Closer to the B side, we have the weight from the cube. So let's say WC for weight of the cube. Okay, let's say this distance is L, so this would be 2L, and the whole thing would be 4L. Okay, so to find the tension here, what we're going to need to do is we know that the force from the bar itself is 165 newtons. And the weight from the cube, that is 185. Now, one thing that we need to do is we have to find the amount of tension in each one of the cables individually. We don't really have a way that we can do this without using something called moments. And we know that this bar is not going to be moving, right? If you're plucking it, like if I pluck a guitar string, it's not going to move the entire structure of the guitar. Similar type of thing here. So the plucking is not going to actually cause any motion. We're going to assume that we are in static conditions right here. Okay, so to find the moment, let's first take the moment about point A. So here can be point A, here can be point B. So moment at point A. Let's say counterclockwise is going to be positive. The sum of all moments about point A has got to be 0. And we're going to pretty much just see here where we're going to, have these, who's going to cause us to try to rotate. That's what the moment is like our tendency to rotate. So our WB is going to try to make us rotate in the clockwise direction. That's negative. So it's going to be negative WB. And we need to multiply it by the distance that it is away from the point at which we're rotating about, or hypothetically rotating about, and that's A. So in this case, it's 2L. Okay, and the next term is our WC, and that's going to be 3 L's away. And also going to be negative because it's going in the clockwise direction. So negative WC and 3L. Okay, and the last one is going in the positive direction, and it's got to balance out both of these. We have the tension B, and that's going to be 4 L's away. So plus tension of B, and multiply that by 4L. 4L, that's for life. Okay, so we can isolate these, and we can solve for TB. As you can, let's first move the W terms to the left side of the equation. So we have positive WB 2L plus 2WCL is equal to TB 4TBL. And as you can see, we can just divide both sides by L, so everyone can lose their L. We don't take no L's around here. Ahahaha. Like that. And then we can quickly erase the L's, and this will be perfectly mathematically valid. Oops, we still need that 2. and that W. But we can also divide both sides by 4 to just get TB. And we know that that's just going to be like 1/2. Whoa, it's 3WC. So it's actually not going to be 1/2. We're not going to be able to factor that out. My bad. So instead, we're going to have 1/2 WB plus 3/4 WC. Okay, and then we just got to sub in these numbers. So WB, our bar, was 165 newtons. Plus 3/4 of WC is 185 newtons. This is our tension in chord B. Okay, so let's do this calculation real fast. Times 165 over 2 plus 0.75, the same as 3/4, times times 185. Cool. So in this case, our tension in chord B is going to be equal to 221.25 newtons. That's our tension in B. Okay, now we need to find our tension in A. We could do it another way with a moment, but another way that we can do this is we just take the sum of all forces, sum of all vertical forces. Okay, we can do that with a situation like this, setting it up like this. So the sum of all vertical forces, with up being positive, we're going to have our two tension forces that are positive. So TA plus TB, and our two weight forces that are going down. And they have to be perfectly equal to each other when they get summed up. Otherwise, this would be moving, and this is not moving. So, yeah, so that's going to be minus weight of the bar minus weight of the cube, and that is all equal to 0. Okay, so we can see that the tension forces balance out to be perfectly equal to the weight forces. And they're both going to be positive once we bring them to the other side. So we just calculated TB. So to solve for TA, this is going to be the weight of the bar, so that's 165 newtons minus plus 185 newtons, not 18, minus 221.25 newtons. And TA, I expect that to be less than TB because it is, more of the weight is closer to TB. So TB should be under more tension. So let's add this up. 165 plus 185 minus 221.25. And my calculation for this is 128.75 newtons. Cool, so that is how we find the tensions, and once we get the tensions, we just need to substitute them into here. Okay, so F is, let me just copy this and bring this down so that it will be easier to deal with. Oops. Okay, technology is cool again. Let's sub in these numbers and see what we get. So let's first find the frequency of A. So let's, under the root, we got our tension of A is 128.75 newtons divided by mass, which is 0.0055 over 0.75, all over 2 times 0.75. Okay, let's calculate this out. Underneath the root, we got so we got 128.75 divided by 0.055, 0.75, and that whole thing divided by 2 times 7.75, so that's divided by 1.5 overall. And the frequency for this is going to be 88.33 hertz. Okay, not tremendously much. You'd be able to hear that. That's really, really low though. So maybe like a low bass guitar note, that would be like what it's like. But that I expect that the frequency for B is going to be higher because B is under higher tension. And as you know, if you play guitar, when your tuners increase the tension in the chords, you get higher frequencies, higher pitches. So let's do that with the frequency for B. Okay, so the frequency of B was 221.25 over the same 0.0055 over 0.75 all over 2 times 0.75 to follow the equation protocol. And let's figure this out. Okay, so conveniently my calculator has some RAM, so it actually remembers the previous calculation. I can just sub out a different number. So my calculation for this, 115.80 hertz. Okay, so it's going to be a slightly higher frequency, but still very, very low. Like you'd be able to hear this, but it's very low, you know. Okay, cool. So that would be the frequencies that they would produce. They're fundamental. Okay, awesome. So we don't really have a solution here, so missing solution. Missing solution. A is 88 hertz. B is 115 or 1.6 hertz. Okay, so the next question that we have on the menu today is asking us how many electrons does it take to make 1 coulomb of negative charge? Okay, this is a fairly straightforward question with a fairly straightforward answer. So the first thing that we need to know is that we have the charge of an electron. We know that this is the charge of an electron is going to be 1.6, negative that is, times 10 to the negative 19 coulombs, and this is per electron. Okay, so if we want to get the number of electrons that make 1 coulomb, well, we know that we have 1 coulomb. Let's just write that as 1C. And we're going to multiply that by the reciprocal of, the ratio of coulombs per electron. So this will be electron over 1.6 times 10 to the negative 19 coulombs. I guess they can both be negative because it would be a negative 1 coulombs of charge. So it's pretty much just, you got to find the reciprocal of this. Okay, so let's do that ASAP fast. The reciprocal of 1.6 times 10 to the power of negative 19. And the result of this calculation, and you see the coulombs cancel out, the result of this calculation is 6.25 times 10 to the power of 18 electrons make 1 coulomb. Now, yeah, and that's it. If you wanted to round this to 2 significant figures, it'd be 6.23, not 7. So, yeah, just a little rounding error. Got to mention that. But otherwise, yeah, it's a good procedure. So, 6.25 should not round to 7. Otherwise correct. Okay, so the next question that we have here is a vector situation. Everything's fun with vectors. So the question is asking us, we're having trouble with this question. Okay, the question's here. So we have 2 vectors. We have A. So let me write out the vector A. I'll write the units outside of the brackets. This could be a nice thing to learn. So 2.4 I and plus 4.5 in the j direction. And that's all meters. And our second vector b is going to be, well, another two-dimensional vector, except it's going to be 4.1 in the I and negative 2.2 in the j. Okay, now we have to compute the following vector quantities. Okay, so a plus b. Well, we just have to add up these components. Well, I terms go with the I terms, and the j terms come with the j terms. Okay, so a plus b. We see that it will be the I terms added together. So 2.4 plus 4.1, that's 6.5. And we are going to have a 4.5 plus negative 2.2. So that's going to be 2.3 plus 2.3 j meters. Okay, so those correspond good to those answers. Now the magnitude of AB, we represent it with like a double absolute value for magnitude. Sometimes you also see it with like a single absolute value. It's just sometimes we get confused with absolute values, so it's better to do double sometimes. But it's just like a Pythagoras theorem situation. 6.5 squared plus 2.3 squared, all under the root. And this shall give us under the root 6.5 squared plus 2.3 squared. It is 6.89. Yeah, good job. Meters. Okay, keep in mind that the units still got to persist, so the magnitude of this sum is meters. Now, the next thing that we want to keep in mind here is what is this actually representing? So if we're going like 6.5, 3, 4, 5, 6.5, 6.5 in the I direction, and then 2.3 in the j direction, like this, in the positive j direction, right? So it's going up. What we're pretty much looking for is this angle right here. So if we want to get this angle, we can see that it will take the inverse tan of 2.3 over 6.5. Okay, so this angle should give us inverse tan divided 6.5, 19 degrees from the positive x-axis. Okay, and yeah, we got the same answer here. So it's likely maybe it wasn't a tan that was used here, or maybe the maybe it was the other way around. Maybe it was reciprocal, but otherwise, like you generally want to like draw this out so you can kind of have a visual idea of what's going on here. Okay, so the second part of this question is asking for the vector b minus a. Okay, so if we want to do, maybe I'll do this in a different color just to show the separation, but it's a very similar procedure. So vector b minus vector a, we're just going to be doing those components individually. So, the I component minus the I component of I, so 4.1 minus 2.4 is 1.7 in the I direction, and in the j direction we're going to have 2.5 minus 4.5. Okay, so that's going to be negative 6.7. Yeah, exactly. And all in meters. Okay, and for the magnitude, let's just write magnitude. Well, we're going to follow the same Pythagoras theorem type of situation. So under the root, we have 1.7 squared plus 6.7 squared. I mean, you could write plus negative 6.7 squared, but the negative neutralizes itself on the squaring, so it's not really necessary. So let's ask our calculator what that is. Make sure that it's right. Okay, here we got 1.7 squared plus 6.7. And I got 6.9, same as you, awesome. So this is equal to 6.9 991 meters. Happy face, we got the same answer. And for the angle, well, it's going to be the same procedure. It's going to be the j component divided by the I component in the inverse tan. Negative 6.7. Don't forget that negative, okay? 1.7. And, okay, so let's take that calculation ASAP fast. Negative 6.7 divide 1.7 is a negative 75.76 degrees. Now, does that correspond? Let me just check real fast if that is the same as, that is just slightly off from this number. It's like actually 284, but it's very, very close. So I'm not sure what procedure that this corresponded to when you calculated this, but very close, but maybe just like a rounding error or something like that going on. But otherwise, yeah, this solution here is good, and, you know, hopefully we got the help that we needed. Cool. Both solution is good. Awesome. Okay, so here we have the next question on the menu today, which is asking us, with a vector sum a plus b plus c, all vectors. So let's write this out as we go. Vector a plus vector b is equivalent to vector c. And we are given vector a, which is like this. Vector a is 13.5 meters with an angle of 37 degrees. And so it's clockwise, so it's like this from the x-axis. Okay. And vector c is given as 15 meters, and it is angled 26.5 degrees. .5 degrees counterclockwise from the negative x direction. That is critically important, negative x direction. Okay, so this is going this way. Okay, so another way that we can write this is 206.5 degrees, because if we just add 180 to it, that would be the same as 200.6. Okay, and we have to find out what is the magnitude and angle of B. Okay, so essentially what we have here is we're trying to isolate for B, and as algebra goes, what we can do here is we can see that B vector is equal to C vector minus A vector. Now, because we are given them in magnitude and angle form, we're actually going to be a little bit easier to deal with. This is going to be easier to deal with if we have if we get it into component form, rectangular component form, I and J form, is what we're looking for. So for A, to convert it, is, well, the I component is going to be horizontal, and that's going to correspond to a cosine. Okay, so cosine 37 degrees times 13.5 in the I direction. I'll write the units outside. And in the J direction, it's also going to be positive. It's going like up towards the upright. So, but it was going to be sine. Okay, so this is going to be plus sine 37 degrees times 13.5 all meters. And to get numerical values for this, let's calculate that ASAP fast. Cos 37 times 13.5, I got 10.78i, and then the same thing but with sine 37 times 13.5, I got this is plus 8.78 13.12 in the j direction. All meters. Okay, and we're going to do the same procedure for the c, except notice how we are going towards the bottom right, the bottom left. That means we have to have a negative y direction and a negative x direction. Okay, so we're going to have negative terms here. So we'll use the smaller angle, the 26.5 degrees, because and we'll just make our sign adjustments as we go. So, but we know both are going to be negative. So yeah, we'll just do that. So this will be cos 26.5 times 15. In the I direction, minus, because we're going towards the bottom left, sine 26.5 degrees times 15 in the j direction. And that whole thing is meters. Cool, so let's multiply that out. Cos 26.5 times 15 negative 13.42 in the I direction, and then minus, now let's find the sign of that. Sign is going to be minus 6.6, oops, 6.69 in the j direction, and that is all in meters. Okay, now we have to do c minus a to find b. Minus a. Okay, so the c component is going to be negative 13.42 minus the a component, which is 10.78. That's I. And then for the j, we will have minus 6.69 minus 8.12 in the j direction. And this will give us our b vector. Okay, so we got 13.42 and 10.78 minus 24.2 in the I direction. And then in the j direction, we're going to be pretty negative with that one. 8.12 and 6.69. That's going to be 14.8 in the j direction. Okay. No, I rounded them earlier, but I'm pretty sure that they would like perfectly line up to be these nice and easier numbers. Cool. So it's asking for the magnitude of b. So to find the magnitude of b, what we will do is represent it like this. This is going to be a Pythagoras theorem type of situation. So it's going to be negative 24.2 squared plus negative 14.8 squared. And that shall be the magnitude. And what will this be? This will be under the root 24.2 squared plus 14.8 squared. And that is 28.37 meters. And it's going to be positive. Magnitudes are always positive. Okay, so that's good. And to find the angle, well, we have to find the inverse tan of this. So the inverse tan is going to be the y component divided by the x component. So the y component is negative 14.8. And the y component and the x component is negative 24.2. Tan inverse. Okay, that's important. 18.8 divided by 24.2. And my calculation for this is 31 just round it off, it'll be 31 degrees. And this is 31 degrees, but we know that we are going in the down left direction. So we know that this has to correspond to 31 degrees this way, which is going to correspond to 180 degrees plus 31 degrees, which is equal to 221 degrees if we are going this way. Okay, so that's going to be the angle of B and the magnitude of B. The calculations here are congruent with mine, so that's awesome. So here, the above solution is good. Awesome. Big high five. Okay, so here we have the next question on the menu today. It is asking us, or is presenting the situation: Richard is driving home to visit his parents. 140 miles of the trip is on the interstate where the speed limit is 65 miles per hour. Normally Richard drives at the speed limit, that's good, but today he's running late and decides to take his chances by driving a little bit faster at 73 miles per hour. How many minutes does he save? And is the savings in minute worth the risk of, being caught for speeding? Because, speeding is serious business. So the first thing that we need to do is identify our information of interest. Okay, so our distance is 140 miles. And our speed limit, so let's call that V for VL for limit, is going to be 65 miles per hour. To me, it makes more sense to write it as a fraction. I know that that's not always common, but it'll make more sense. You'll see why. And then the VF for V fast, this is going to be 73 miles per hour. Okay, so what we know here is that time, distance over time is equal to velocity, right? And we're trying to find for time, so it's just going to be distance over velocity is equal to time. We're looking for the time difference between our fast and our slow, right? But they're going to have the same distance overall. So to set up that difference in time, what we can do here is our time of our slow, or our time of our limit, minus the time of us going fast is going to be, the time saved. Time saved. And subbing this relationship into here, we know that d over the velocity of the limit is minus d over the velocity of the of going fast. That is going to give us a t saved. And the unit cancellation would work out. That's why I mentioned the divided by h. Now we just got to sub in these numbers, and we will get our hours that are saved, and then we'll just convert our hours into minutes. Okay, so in both of these cases we have d, so we can actually factor that out. 1 over VL minus 1 over VF equals time saved. Okay, and let's calculate this. So our distance is 140 miles. And here we're going to have hours per mile. Our slow is going to be 65. And our fast is going to be hours per 73 miles. Okay, so let's send this to the calculator and figure out what that is going to be, and our results will be in hours because, as you can see, our miles out here, they're going to cancel each other out. So 140 multiplied by, in brackets, 65 reciprocal minus 73 reciprocal, and my results for here for, oops, you can't see that, time saved is equal to 0.236 hours, and multiply by 60 to get minutes, 60 min per hour, and then the hours will cancel out. Multiply that by 60 and you will save 14 minutes. 14.16 minutes. Saved. Okay, so yeah, that will be how many minutes you saved. My calculation was a little bit different, but that's likely because I did not actually round it here and then keep doing the math with the rounding. But you know, the process is right. It's just sometimes it's better to do the actual algebra all in your calculator instead of having these intermediate rounding that are going to slowly introduce errors that are going to cause these you know, these small differences to happen. But otherwise, it's something interesting to think about. You increase your speed for 10 miles per hour, but you only end up saving 14 minutes. So, you know, you're risking speeding tickets and all that just to save 14 minutes. Is it worth it? It's up to you. Don't be speeding. I don't recommend it, but you know, that was what Richard did, and it is what it is. Okay, so the above solution is good. Very good. Okay. So the next question that we have on the menu today is presenting the situation where we have two identical ions. So those are just charged items. So the electrostatic force between two identical ions that are separated by 5 times 10 to the negative 10 meters is 3.7 times 10 to the negative 9 newtons. Now we have to find out what is the charge of each ion, how many electrons are missing from each ion, and how far apart must two protons be so that their electrical force, their repulsive force, is equivalent to gravity on Earth's surface. Okay, so let's handle this question one at a time, 1 point at a time. Okay, so the first part of the question is presenting this situation. We have two ions, so we got a charge Q here and a charge Q here. We know that their separation distance is 5.0 times 10 to the negative 10 meters, pretty close together. And they have a force. Let's make a blue force. The force that they feel is going to be like this. Identical ions means that they are going to be repulsive because that's why they're trying to get away from each other. If they were opposite charges, they would be trying to get closer to each other. But the key thing here, identical ions. So they have to have a repulsive force between them. Okay, and the force of this is equal to 3.7. Whoa, let's not scroll down like that. 3.7 times 10 to the negative 9 newtons. Cool. Okay, so what we're trying to do is we're trying to solve for the charge on each ion. And let's get back to my black pen here. We know that Fe is equal to Kq times Q over R squared. In this case, Q's are the same. But we're trying to solve for the Q. Okay, so in this case is Kq squared over R squared. So we just got to isolate for the Q. So that's going to be Fe times R squared over K, all under the root, is going to give us RQ. Okay, let's sub in these numbers. By the way, K is equal to 9 times 10 to the 9. That's Coulomb's constant. It's a good thing to keep in your mind. Okay, so let's sub in our numbers. 3.7 times 10 to the negative 9 times our distance of separation. So that's 5 times 10 to the negative 10, but all squared. All divided by 9 times 10 to the 9. And that's all under the root. Cool, so I'm going to pull out my calculator and figure out what this calculation is. So we got 3.7 times 10 to the power of negative 9 times 5 times 10 to the power of negative 10 and that's squared, and then divided by 9 times 10 to the power of 9, and that is divided out. And the result of this whole thing is under the root. So, okay, so my calculation for the charge Q is 3.205. We only got two significant figures, so that's what I'll need to leave it as. 3.2 times 10 to the negative 19 coulombs. Okay, so this will be the charge of ions. Okay, and then the next part of the question, well, that's part A. Part B of the question is how many electrons are missing from each ion? Okay, so if this is the charge between them, we know that the charge of an electron charge, this is 1.6, or negative that is, but let's just keep it as absolute value. So positive, or maybe, but just better not to write that at all if we're doing absolute value. Oops. Let's get my pen back. 1.6 times 10 to the negative 19 coulombs. So since that these are charge is double electron charge, must be 2 electrons. 2 electrons missing, that is, or 2 electrons gained. All right, so there could be 2 electrons missing. There could also be negative 2 electrons missing because, you know, we have some like metals like to lose electrons, and you know, things that are closer to the right side of the periodic table, they tend to gain electrons. Okay, so it must be 2 electrons away from neutral. Okay, we don't know if they're gained or lost. Okay, so that's just a little bit of chemistry. It's not necessarily mandatory. I'm sure if you said 2, you'd be fine just there. Okay, the next part of the question is how far must 2 protons be if the electrical repulsive force acting on them is equal to its weight on the Earth's surface. So, okay, so this is what question 3 is asking us, or part C of this question, is pretty much the force of gravity on a proton is going to be equal to the electrical force of repulsion between 2 protons. Okay, so we know that the gravitational force is just mass times the acceleration due to gravity, and this is going to be kq squared. We have 2 protons, they're clones of each other, they're going to have the same charge, over r squared. Okay, so it's asking us what is the distance between them for this to be possible. So we're pretty much trying to solve for r. So r squared is equal to kq squared over mg. And r is going to be, well, we send that all under the root, kq squared over mg. Now the mass, to sub in these numbers, we know that k is going to be 9 times 10 to the 9, nice and easy. Q is going to be the charge of a proton, which is the exact same as the charge of an electron, so 1.6 times 10 to the negative 19 coulombs. The mass of a proton, if I remember correctly, is 1.27 times 10 to the negative 27. I think. 1.67. Ah, so close. Negative 27 kilograms. And the acceleration due to gravity, that is 9.8 meters per second squared. 9.81 meters per second squared. Okay, so subbing all of these into our equation, we will get a situation like this. R is equal to, under the root, we have k, 9 times 10 to the 9, multiplied by q squared, 1.6 times 10 to the negative 19, all squared, divided by mass, 1.67 times 10 to the negative 27, multiplied by gravity on the downstairs, 9.81. Okay, so let's calculate this out, see what we get. So on the upstairs, we got 9 times 10 to the power 9 times 1.6 times 10 to the power negative 19 squared divide by 1.67 times 10 to the power of negative 27 times 9.81. Actually divide by 9.81. And all of that under the root. And my calculation for R is 0.118 meters. Okay, hopefully we found a similar result here. Exactly. Cool. So this would be the separation that would be required for that. Awesome. So yeah. Yeah, that addresses all of the points of interest of this question, so we can call that a question complete. Awesome. Big high five. Okay, so the next question that we have on the menu today is presenting a situation where we have 4 point charges, all with the same magnitude of charge of 2.5 times 10 to the negative 12 coulombs, are fixed to corners of a square that are 4.6 centimeters on each side. Okay, so let's actually draw the situation. At 4.6 centimeters. And this is 0.0046 meters. The same thing as 4.6 centimeters. It's that's actually not the same. I got an extra 0 in there. My bad. 0.046 meters. Okay, that's the same. 3 of these charges are positive and 1 is negative. Determine the magnitude of the net electric fields that exists at the center here. Okay, so if 3 of them are positive and 1 of them is negative, let's call this one the positive, this a positive, this a positive, and this a positive. And I'll actually change this one up here to be a negative so that it lines up with the diagram that we have down here. Okay, so because this little point in the middle is going to be is perfectly in the middle, we know that the forces here blue forces cancel out. They are perfectly the same charge and the same distance away from each other. So if we were to incorporate them into the same calculation, it would be, you know, they would neutralize each other. One would be positive and one would be negative, and you know, they would perfectly be equal to each other. So the result of those net blue forces is 0. But you know, if we have the green forces here, we can see that this would be going that way, and this is also going that way, right? So the positive is like the convention is the direction of the force is what direction a hypothetical positive charge would be pushed. Beside a positive Q is going to get away, beside a negative Q is going to get closer. But since the magnitudes of the charge are going to be the same, we know that green forces, net green force are same. Net green force is double 1 green force. Okay, cool. So how we determine what the green force is, we're going to first need to do some trigonometry, okay? Because right here, you can see that this is going to be 0.023 meters. And this is also going to be 0.023 meters, just because it's like halfway for the square. We're going to need the hypotenuse. Okay, so the R in this case, or actually our net force, our magnitude of our net force, is going to be 2 times K Q net electric field, all right? So my bad. So it's going to be field. Okay, so it's just going to be 2kq over r squared, and r squared, or r on its own, r squared is actually going to be the hypotenuse, so it's just going to be 0.023 meters squared plus, well, 0.023 meters squared. Okay, so we can just sub in our numbers and we can find our net force here. So 2, K is Coulomb's constant, 9 times 10 to the 9. Our charge is given as 2.5 times 10 to the negative 12. And r squared down here, well, it's just going to be 2 times 0.23 squared. (0.023 meters squared). Okay, so the 2's cancel out, so it's going to simplify the math a little bit. So let's calculate this out. 9 times 10 to the power 9 times 2.5 times 10 to the power negative 12, all divided by 0.023 squared. Should be electric field, so it should be an E. So the net electric field is going to be 42.53 newtons per Coulomb. Okay, that's going to be the magnitude. Hopefully we came to a similar conclusion here. Most likely just going to be a rounding error here with the calculation of R. But yeah, same ballpark. So it's most likely just a rounding error. So yeah, the solution is good. Awesome. Awesome. Above solution is good. Good job. Okay, so here we have the next question on the menu today, and it is asking us, a right triangle has side lengths of 4 and 5 meters. Okay, so the non-hypotenuse of a right angle triangle looks like this. It's not quite to scale, but here we have 4 meters. Here we have 5 meters. Here we have hypotenuse. What is the hypotenuse of the triangle, and what is the angle between the 4 meter and the hypotenuse? Okay, so like this. Okay, so let's start with the angle, because that's going to be fairly straightforward to do. So we know that the relationship, thinking back to our trigonometry, tan theta is going to be equal to our opposite over adjacent. Okay, so if we wanted to find theta, we would just do the inverse tan. And what's our opposite in this case? Our opposite is 5. Our adjacent is 4. Okay, so this angle, let's do that ASAP fast. Inverse tan of 5 divide 4, 51 degrees. 51.34 degrees. So what we got here It sure is. Good job. Okay, and to find the hypotenuse, we got to use Pythagoras' theorem. Pythagoras was a very smart guy in ancient Greece. He really liked his triangles. Okay, so we know that, oh, not under the root. So h squared is going to be the sum of 4 squared plus 5 squared. So 16 plus 25 is 41. So h is just going to be the square root of 41. This is the accurate answer, but a approximate answer is, well, we'll ask our calculator to calculate that, and we'll just round it off. So it will be approximately, h is approximately equal to 6.403 meters. Okay, units matter as well, but yeah, this would be our answer for that. Okay, so this perfectly describes a triangle, and we can easily calculate this, since we know that this is this angle is 51 and this is 90. This will be just around 39 degrees or 38 degrees or so. Okay, otherwise this solution is good. So nice. Is good. Awesome. Okay, so here we have the next question of the day, and it is asking us, or is presenting a situation where we have a long insulating massless rod of length L, pivoted at its center, balanced with a weight W at distance x from the left. Okay, so this diagram is not particularly clear, so I'll redraw this ASAP fast. So let's say that this is our balance point of our situation. And here is our massless rod. On either end of it, we have positive Q on the left side. We have positive 2 Qs on the right side. Okay, and here we have capital Q, which is positive, and here we have capital Q, which is also positive. And the distance between them is h. This length here, the length of this whole unit is L. And x distance away from the whole left side passes the center point is a weight. Okay, now the weight is not given, and the charges are not given, and neither are the distances. Okay, so we're going to be pretty much entirely in the realm of algebra as we solve this question. Okay, but this is the situation here, and that's the pivot point. Okay, so part A of the question is asking us, find the distance x for the position of the weight when the rod is balanced. Okay, so when the rod is balanced, that means that the net forces are going to be 0 in the vertical direction, and as well as the moment about the center is going to be 0 as well when this is all in equilibrium. Okay, so to represent that, let's say we want to find the moment. Moment at center. To do that, we want to do something like this. So if we say that counterclockwise is our positive direction, as is a typical convention, at least here in North America, So the moment about C for the center is going to be 0. Okay, so who's thinking about here? We know that these two Q's, they're both positive, and they're going to try to repulse each other. So let's draw in our force here. So Fe for electric force, FEL for the left electric force, and here we're going to have FER for the right electric force. And here, let's just call that our weight force, and those are the only forces, the main forces of interest here. And of course, we're also going to have like a normal force at the pivot here. So let's just draw that in to be 1000% complete. But here, this is going to be point C for center. Okay, so taking a look at the left force here, let's see how this is going to have a moment. It is going in if this force was to like try to cause us to rotate, it would cause us to rotate in the clockwise direction. That's going to be a negative term. So that's going to be negative FEL, and it's going to multiply by the distance that it is away from the center. So that is 1/2 of L. L over 2. Okay, now we're going to look at the weight force. The weight force is also going to try to bring us clockwise, so that's going to be a negative term as well, and it's going to be a different distance away. It's going to be x minus 1/2 of L, because that's the distance from center that it's going to be. Okay, so this is going to be a negative weight force times L over, nope, the other way around, x minus L over 2. Okay, and the last one is FER. This is going to go in the counterclockwise direction. This is going to give us a positive term here, and it's going to be 1/2 L for distance. So this will be positive FER times L over 2. Okay, so this will be our equation here, and we're looking for the distance x. So to isolate for the distance x, we just need to, well, multiply this all out and do it that way. Okay, so here we're still going to have 0 is equal to FEL times L over 2 minus WX plus L over 2 W plus FER L over 2. Now we're going to try to solve for x, so let's bring that WX term to the other side and divide the whole thing by W. So x is equal to 1 over W times FEL times L over 2 plus L over 2 W plus FER times L over 2. I think that L over 2 could be factored out, but this would be an expression for x. Okay, and yeah, let's actually just factor out the L over 2 for good measure. L over 2W F, the electric force on the left side, plus W plus FER. And yeah, so calculating the forces here is also not particularly difficult. We know that FER is just going to be, or FE in general, just electric forces, is going to be equal to K times Q1, Q2 over R squared. Okay, so finding those, we're just going to like substitute out the F to be in terms of Q's and the R. Okay, nothing too hard with that, but we'll leave it like this just for simplicity's sake. Okay, so that is addressing part A, and that will be X. Part B is asking us, what value should H have so that the rod exerts no vertical force on the bearing when balanced. Okay, so essentially what that means is that the repulsive forces from both of the the charges here, they're going to have an electric force that is like pushing them up. So when is the upwards push from both of these going to be equal to the weight force? Because that would be the only way that there's no force on the bearing or the the pivot point itself. Okay, so essentially what that means is we need to make our weight force equal to our left electric force plus our right electric force. Okay, now let's just square this off. This will be part 1. Our left electric force is going to be big Q and little q. So that's going to be K Q over h squared as the distance between the charges, plus K. Now the right side had 2Q, so that's got to be incorporated here. So 2KQ big Q over h squared. We can put these together because they actually are the exact same. So this will just be equal to 3K little q big Q over h squared. And we're trying to solve for h, right? So what we're going to need to do here is just multiply both sides and divide by w. So h is equal to 3K big Q little q over w, all under the root. Okay, so this will be the height necessary for this to have no net force on the bearing itself. Okay, cool. And yeah, that would actually answer the whole question. Okay, so hopefully we came to a similar expression here. So here we have is equal to K Q squared over h to the power of 2 times L over 2W. Looks fairly reasonable. And for the other one, we actually this process to do this actually would be better to do this with moments. Okay, cool. So yeah, awesome. Using moments, or finding the moment, about the center of the bar. Okay, so for the next question on the menu today, we have the situation where we have two blocks, each with a mass of 4.20 kilograms, nice, are fastened to an elevator. If the elevator accelerates up at 1.6 meters per second squared, find the tensions in the two different cables that are supporting them. Okay, so let's draw a diagram for this, and then we'll talk about part B later. Okay, so here we have a cable, and we have two blocks. Okay, so here we have M1, and this is 4.20 kilograms. This is tension 1, and in here, secured directly below that, M2, we have another 4.20 kilograms. And yeah, That's the situation. The total acceleration upwards is 1.6 meters per second squared. Okay, and this will be tension 2. Okay, so let's actually draw the forces in this and kind of make like a free body diagram of what's going on here. So here, of course, we're going to have the force of tension itself, T1. Here we're going to have the force of tension itself, T2. Here we're going to have FG2, and we're also going to have FG1 here. And we're also going to have the tension is 2-directional here. Okay, so given this, let's take a look at just the first block on its own. The top block. Or maybe the bottom block. I feel like that'd be a little bit easier. So the bottom block. So we only got 2 forces on the bottom block. We have the tension pulling it up and the gravitational force going down. T2 and mg. So we know that the net force of this is going to correspond to oh, you can't see that. So the acceleration upwards is going to be 1.6 meters per second squared. So as a result of this, we know that the net force is going to be the mass of the second block times A that was given to us, and that's going to be equal to the tension force minus the mass of gravity. The gravitational force. Okay, so to solve for this, we're trying to solve for T, so that's just going to be M2A plus mg is equal to T2, factoring, those m's are the same, so that's going to be m, and then A plus g is equal to T2. Subbing in the numbers, we have T2 is equal to, mass is 4.20 kilograms, times 9.81 meters per second going down, plus meters squared, plus 1.6 meters per second squared. Okay, originally they were going opposite directions, but after the algebra they're going the same direction, so let's math that out. And it also makes sense because you would expect that the tension, to pull it upwards, it has to be more than gravity. So 4.2 times 9.8 plus 1.6, those are in brackets, and we have equals 47.88 newtons of tension in T2. Okay, now that tension T2 is also going to be felt at the bottom of T1. That's why we decided to go with T2 before we went for T1. So now let's talk about the top block. On the top block, we have the upwards tension, we have the mass, and that's 4.20 kilograms. We have the force of gravity, mg, and tension 2. So, because the top block has to be providing that tension. Otherwise, well, it's not going to, the second block, the lower block, is not going to go upwards if the top block is not supplying tension to it at all. So this is, that explains the diagram here. Okay, so let's sub in our numbers. So with the same procedure, we know that our mass times acceleration is going to be equal, and our acceleration being 1.6 meters per second squared upwards. That has to be equal to our tension 1 minus our weight force minus tension 2, because Well, if you're trying to go upwards and you're bringing up someone else with you, of course you're gonna need more work to have the same acceleration. Okay, now we're trying to solve for t1 here, so what that's going to mean is ma plus mg plus t2 is equal to t1. Seems about reasonable, and this is just going to be a plus g plus t2 is equal to t1. And let's sub in our numbers. We know our mass is going to be 4.20 kilograms. Our acceleration upwards, 1.6 times 10, it's just 1.6, my bad. Meters per second squared, plus 9.8 meters per second squared, plus T2, and T2 was 47.88 newtons, and that's equal to T1, and I have a feeling that this is just going to be double the last one. Yeah, it actually just is double the last one. That makes sense. The top one is supporting double the weight, is supporting 2 identical blocks, and the middle and the lower one is only supporting 1 of the blocks. So it actually seems pretty reasonable to me that it would just be perfectly double. So this is going to be T1 90. Oops, you can't see that. 95.76 newtons. Okay, so that's going to be the T1 tension. Hopefully we have a similar calculation here, precisely the same. Awesome. Okay, so now let's look at part B. So if the strings can withstand a maximum of 97 newtons, what is the maximum acceleration before the first string breaks? Okay, so the maximum here, we can actually see that the tension in T1 is just going to be like double T2. So if to solve for that, okay, so part B, we are going to need maximum acceleration to stay under 97.0 newtons of force in the cable. Okay, so we are still going to have our original equations. So we know that our total mass so M1 plus M2. So our total mass that is going to be supported times upwards. So let's just leave that as A for now. Acceleration to solve for. This is going to be equivalent, like we're going to set it up in the same way. It's going to be, the tension upwards. Whoops, it's not going to be the total mass, my bad. It's just going to be one of the masses. It's going to be equal to the tension in one the minus mass times gravity minus tension 2, and we know that tension 2 is pulling its original equation out, it's going to be mass times acceleration that we're trying to solve for times gravity. Minus mg, so this is minus m a plus g, and here we're going to have ma, so we're just going to try to solve for a. So tension 1, we know that it's going to be a maximum of 97. But let's actually just algebra this out so that we can isolate A first. But we know that T1 is just going to be 97. Minus mg minus ma plus mg. Actually, minus mg, my bad. Some minus out front. Okay, isolating for we have 2ma is equal to T1 minus mg, minus 2mg actually, and divide everything by 2m. So A is going to be equal to T1 over 2m minus g. Okay, so subbing in all of our numbers, we're going to get A is equal to the top tension. That's going to be 97 newtons. 2 times the mass, 4.20 kilograms. And minus 9.8 meters per second squared. Okay, let's figure this out. 97 divided by 2 times 4.2. That whole thing minus 9.8. And A is, my calculation for that is 1.747 meters per second squared, slightly higher than what we did before, but that makes sense because our tension is going to be slightly, like our tension limit is slightly more than our previous acceleration. Okay, so this definitely looks like and feels like a reasonable answer, so we're most likely good on that one. Okay, so hopefully we have the same answer down here, 1.747. That's awesome, and that's a question complete with precision. Above solution is good. Awesome. Okay, so here we have the next question on the menu today. It is presenting a situation where the person walks up a stalled 19-meter long escalator in 96 seconds. Okay, so a stalled escalator, that just means stairs. It's not moving. We have 19 meters in 96 seconds. Okay, cool. Standing on the escalator and moving, so escalator only. I'm going to assume that it's the same distance. We're talking about the same escalator here, hopefully. It's going to be 19 meters, but in 60 seconds this time. $60 seconds. So the question is asking us how, this is walking. We want to know how fast will we reach the destination, if walking on a moving escalator. Okay, so essentially what we're going to try to do here is find our walking speed, find our escalator speed individually, add them together, and that will be our walking on escalator speed. And using that and the distance, we could easily figure out exactly how long it's going to take if we're walking on the escalator. And I'm going to expect that it's going to be less than both of these. It's going to be less than a minute. Okay, so our walking speed, so our VW for walking is just going to be 19 divided by 96. (19 meters per 96 seconds), and our escalator speed, let's call that VE, is going to be equal to 19 meters per 60 seconds. I'm not doing the calculation right here because I don't want to be rounding them and introduce error into our calculation. Our total speed is going to be equal to our walking speed plus our escalator speed, and the time that it will take is going to be equal to our distance over our total speed. Okay, so subbing in everything, we get 19 meters over our total speed, which is 19 over 96, plus 19 over 60. Okay, and this will give us our time. This really is this simple. Okay, so let's math this out. So let's do the downstairs first. Or we can just do the whole thing in one step. 19 times 19 over 96 plus 19 over 60. That's actually pretty slow because 19 meters is not that far to be going in like a minute, but it is what it is. And the result of this calculation is 36.9 seconds. But to two significant figures, maybe it's better to say 37 seconds. Seconds. Okay, because everything was given in two sig figs, so that should be what we have in the end. Okay, so yeah, exactly. So this calculation is good. Just got to, the main concept to focus on here is that the addition of speeds. So the above solution is good. Very nice. Okay, so for the next question that we have today, it is asking us, what is the acceleration of an object sliding down a frictionless inclined plane in terms of acceleration due to gravity? Okay, so let's actually draw maybe a situation of what this looks like. So here we have like a ramp or an inclined plane with an angle of theta. We don't know what it is. We're trying to find the acceleration in terms of theta. Okay, so let's say we got a slider, or maybe let's say we have a skateboarder because we want to represent something without friction. Nice skateboarder. So we want to represent this as like a free body diagram. Okay, so let's consider what forces we have. It says frictionless, so there's no friction here, which is nothing to be, which is cool. No friction. That's just going to be an additional step, but we're not going to need to do that. So we have our straight down gravity force, Fg, and maybe as a green force, we have our normal force, Fn. Now, if we zoom into here and maybe draw like a line like this that is perpendicular to the surface of the ramp, we can see that if we define our axes like this, maybe this is x and this is y, we're only going to have an acceleration in the x direction. We're only going to go down the slope. We're not going to be like, sinking into the slope, right? That would be like a non-zero y net force, but we have to have a zero y net force. The only resulting force is going to be in the x direction. Okay, so what's going to happen here is we know that our gravity, we can break this down into components. Let's make the components a different color, maybe in red, like a raspberry. Here we have our FGY, And here we have our fgx. We know that fgy has to be equal to fgn. Fgx is only unbalanced force. And we know that this angle here is going to be the same as the angle of the slope. So if we wanted to get the fgx component, this is just going to be equal to our mass times gravity. That's the regular Fg. And then we have to multiply by the by sine angle. Sine of the angle of the slope. Okay, so that's pretty cool, fine and dandy. And if we wanted to extract the acceleration, divide out mass for acceleration, we get A is equal to G sine theta. Okay, so the acceleration due to gravity multiplied by the sine of the angle, that will give you your acceleration down the ramp. Okay, and that is precisely what we have down here, and that is awesome. So yeah, the above solution is good. Here's good. Awesome. Big high five. Okay, so here we have the next question on the menu today, and it is presenting the situation where we have a triangle where we have one charge like this, charge A, which is 9.6 microcoulombs, 9.8 actually, which is equal to 9.8 times 10 to the negative 6 coulombs. And we have point B over here, and point B has a charge of negative 1.4 microcoulombs, aka 1.4 times 10 to the negative 6 coulombs. Okay, and we have point C, that is kind of like, you know, if this was a right angle triangle, C would be where the right angle is. C has no charge. And the distance between these two, let's call this RAC. Here we have 2.1 centimeters, also known as 0.021 meters. And this distance over here, well, similar arrangement, different distance, 9.6 centimeters, 0.096 meters. Okay, always great to do these conversions ASAP fast and do all your calculations in base SI. The question is asking us, find the electric potential at point C. So to do this, what we have to do is electric potential equation. It looks like this. So it's represented with the letter V. It's also commonly referred to as voltage. But we say electric potential for like more of these electrostatic type of questions, and we say voltage more for like electric circuits. But you know, you'll see that plenty, I'm sure. To calculate this, this is just K Q over R. Oh, this distance, let's call this BC. BC like because. Okay, so essentially what we just got to do is the total electric potential at point C is just going to be the electric potential as a result of A at point C plus the electric potential as a result from B on C. To do this, well, it's just going to be K QA over RAC. Right, it's not squared on the bottom, right? Yeah, awesome. And plus K QB of RBC. Cool. So if we see that we can factor out the K term to make this calculation just slightly easier, less typing in the calculator, which is good because every time you type into your calculator, you have the risk of hitting a wrong button, and only one wrong button press is enough to crash the boat. So, if you set up your algebra so that you have as little typing into your calculator as possible, the better it is, and it'll also be faster. Not only about precision. Okay, so let's sub in our numbers and figure out what in the world this electric potential value is going to be. Okay, so our K value, that is 9 times 10 to the power of 9. Coulomb's constant. It's a good thing to memorize, but you'll most likely have it on an equation sheet if you see this in a test. Okay, and then we have QA. That's a positive one. We got to keep these signs, front and center in our mind, times 10 to the negative 6 coulombs. Over the distance between A and C, that is 0.021. I'm about to turn 21. Fun fact, it's almost my birthday. Cool. And then the second one is going to be QB, which is negative. Don't forget the negative. If you forget the negative, it's going to hurt. Okay, so let's incorporate that. Plus negative 1.4 times 10 to the negative 6 coulombs. And that distance is 0.096 meters. Cool, so let's send this to our calculator and figure out what this is going to be. 9 times 10 to the power 9 times 9.8. Oh, this all got to be in brackets. Ten to the negative 6 divide by 0.021 minus, don't forget the minus, 1.4 times 10 to the power negative 6 divided by 0.096, close the brackets, and I got an electric potential calculation that is pretty large, can't lie. Oops. It's equal to 4,068,750 volts. Yeah. So yeah, we got precisely the same calculation here. So yeah, this is how you do it. The calculation is agreed here, and yeah, everything's good. So good job. That seems pretty high. Like that would be like your wall is only 120 volts. So that is quite the electric potential here, but that is like like microcoulombs is a decent amount of charge, and centimeters away, that is very, very close. So it does seem and feel like a reasonable answer. So yeah, cool. So nice. So here we have the next question on the menu today, and it's asking us, or is presenting the situation where we have a parcel of air. You don't need to really worry about what this object is. You can imagine it as like, a tennis ball or whatever other type of object. It's because it's tough to visualize moving air, but the math is all the same. So it is moving in a straight tube with a constant acceleration of negative 4.3 meters per second squared, and has a starting velocity of 12 meters per second at 10:05 a.m. I'm going to assume that's 10:05 minutes with 0 seconds. And so the first question is, what is the velocity at 1 second later? Okay, so let's actually draw out some of the given information that we have here. So our acceleration, negative 4.30 meters per second squared. Our initial velocity, let's call that V1, or VI for initial, is going to be positive 12.0 meters per second squared. And our initial time, so TI, is going to be 10:05 a.m. 0 seconds in. And I guess I don't really need to write AM because all of the other things are in AM, so it doesn't really matter. AM or PM is the same thing. Okay, so for part A, it's asking us what is the velocity at 1 second later. So part A, what we need here is our kinematics equations. Our final velocity, we know, is VF is equal to our initial velocity plus our acceleration for, however long that we do this. Okay, our delta T in this case is going to be TF minus TI, which is, 10.100501 seconds minus 10.0500 seconds, 1 second. Okay, so if we sub in our numbers, our final velocity here is going to be our initial velocity, that's 12.0 meters per second. Now we're going to add a negative number to it. That's nothing to worry about. That just means we're decelerating. Kind of like when you pump your brakes on your car, that's a negative acceleration that's happening. Multiply by the time, 1 second. Okay, so that's a quick math. VF is just going to be 12 minus 4.3. And that is 7.7 meters per second. Under that type of deceleration. And it's constant, okay? So we're always going to have that. Is that what we got here? That's not the acceleration. Okay, so I guess they just used the wrong acceleration value. That's nothing to be too worried about. Here, now it's going to ask what is the velocity at 4 seconds after here. So part B is just going to be the same, except this is going to be 4 seconds instead of 1 second. Part B, we're going to have the final velocity is equal to our initial velocity plus acceleration times our change in time. In this case is 4 seconds, so it's going to be 12 meters per second plus negative 4.3 meters per second squared times 3. Oh, you can't see that, my bad. Times 4 seconds, actually, my bad. Okay, so in this case, 12 minus, in brackets, 4.3 times 4. I guess we don't really need brackets. This is going to be negative 5.2 meters per second. Okay, so essentially you were going here, but you were decelerated so much that you started to go in reverse. It's pretty much what's going on here, and if they're still using the same value here, unfortunately that's not going to be possible. And the next part of the question is asking us what is its velocity 1 second before here. So in this case, for part C, we're going to have VF is, well, it's the same equation as before, plus A times delta T, except our delta T in this case is going to be negative. We're going in the past, so negative 1 second, because in the past. Okay, so our initial velocity, that's still going to be 12 meters per second, plus negative 4.3 meters per second squared. That's our deceleration. and multiplied by -1 seconds. Okay, so you see those negatives cancel each other out. So this is just going to be 12 plus 4.3. That's going to be VF equals 16.3 meters per second squared. Okay, and that's going to be the velocity 1 second before. Okay, cool. So that addresses part C of the question, and part D is describe the shape of the graph of velocity versus time. So as you can see, this kind of has like a y equals mx type, mx plus b type of feel to it, because you see that a is going to be constant, vi is going to be constant, t is going to be our only variable. So essentially what this graph is going to look like is, if here is our velocity and this way is our time, essentially it's going to look like a linear straight line like this. And the slope of this is going to be the acceleration, which is going to be -4.3 meters per second squared. Okay, so yeah, that will be what the graph looks like. Just a downwards line for the deceleration. If it was a positive acceleration, it would be an upwards line and the slope would be positive. Okay, so yeah, cool. And the last part of the question, argue for or against the following statement, knowing that a single value of an object's constant acceleration is like knowing the whole list of values for its velocity. And that is absolutely correct, because as long as we have one like starting velocity knowledge point, we can calculate at any point in time. So even if we were going like 1,000 years in the past, assuming a constant acceleration, we can calculate exactly what that velocity is going to be. Okay, so cool. This addresses this part of the calculation, and yeah, awesome. So the only thing that I got to mention here is that calculations were done, acceleration as 3 instead of -4.3. Process is good. Calculations are off. Oh man, that was the last question. Time flies when you're having fun, as the old saying goes. So those are all the questions that we have for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you're interested in submitting your own questions, or if you're interested in getting some help with your homework or getting some help with some tutoring, we have links in the description that can help you with that. And if you enjoyed today's video, a like would be greatly appreciated. And if you really enjoyed today's video, we would definitely appreciate it if you shared with your friends. This has been Millan from OneClass. Today has been a great time with the physics. I had a great time, and I hope you had a great time as well. Remember that physics will never do you wrong. Physics is, it's always a good time. And yeah, stay safe, stay positive, and have an amazing rest of your day or evening or morning, whatever time you're watching this. Take care and keep on physicsing.